Hello, in this video we'll start to learn how to represent permutations of finite sets using one-line notation. So of course one way to express a bijection between two finite sets is graphically. On the left we have the domain, on the right we have the codomain, and I've drawn an arrow between each element of the domain to its corresponding element in the codomain. So you can see here that f of 1 is b, f of 2 is d, f of 3 is a, f of 4 is c, and f of 5 is e. Note, of course, this approach of defining the function by telling you exactly what it does to each element of the domain also defines the function. So these two approaches are equivalent. But of course, drawing this picture for each permutation is going to be very, very complicated. In particular, you can imagine trying to write a paper doing these examples with these pictures would be impossible. So it would be good to have a shorthand. And the shorthand, one of the first shorthand approaches for writing down a permutation is to do the following. So assume that you've ordered the elements of the domain as follows, 1, 2, 3, 4, 5. Then that will be the first row in this table. Then the second row would be the outputs of the function. So the first entry would be f of 1, which is b. The second entry is f of 2, which is d. Then we write down f of 3, which is a. Then f of 4, which is c. And finally f of 5, which is e. So you get b, d, a, c, e. And so sometimes we just get rid of the first row entirely and we just write down the bottom row, which looks like a permutation that you would see in a discrete math or combinatorics course. Just a list of elements. Every element appears exactly once, and order matters. And that's the context in which we use the notion permutation and why we call these permutation groups. So look, now you have a way of writing down a permutation that you can actually type on a typewriter. No pictures needed. And so, for example, if I wrote down the permutation 3, 1, 5, 2, 6, 9, 7, 8, 4, and I asked you what is f of 6, what would you do? And this was f. You would look at the sixth entry, 1, 2, 3, 4, 5, 6, and you'd tell me it's 9. Similarly, if I asked what is the third entry would be what's in the fifth spot. It's 5. Likewise, if I asked you what's f inverse of 8, that would be asking where does the 8 appear? And the 8 appears in this case in the 8th position. As another example, I could ask you, where does the 3 appear? Well, the 3 appears in the first spot. Right, that's where the 3 appears. So, given the permutation, you can compute its value at points. You're just looking at, look for that position in the list, and then write down the entry appearing in that spot. And likewise, you can compute the inverses. Look for where a number appears in the list and write down which spot it appears in. And in particular, we can write down f inverse here completely. Where does the 1 appear? The 1 appears in the second position. The 2 appears in the fourth position. The 3 appears in the first position. The 4 appears in the last position. The 5 appears in the third position. The 6 appears in the 5th position. The 7 appears in the 7th position. The 8 appears in the 8th position. And the 9 appears in the 6th position. 7 and 8 are both kind of interesting because f of 7 is 7 and f of 8 is 8. These are what you would call fixed points. And so this is one way to denote bijections, is by what's called one-line notation. That's what this is called. The two-line is when you actually include both rows. And you can see that given one-line notation, you can compute a function value and its inverse. You can also compute composition of two functions, which is what I will do next. So let's go back to our more graphical depiction. Suppose this was f and g. Then if you wanted to do things visually, what does g composed with f do? Please note the way our function notation works. If you're going to apply f first and then g, then the corresponding function notation is g composed with f. That's a holdover from how we denote functions, unfortunately. But we see, what does 1 do? 1 gets sent to 2 and then back to 1. So we see that 1 is sent to 1. 2 gets sent to 4, which gets sent to 5, so 2 is sent to 5. 3 gets sent to 1, which gets sent to 2, so we see 3 goes to 2. 4 goes to 3, which goes to 3, so 4 goes to 3. And finally, we should see that 5 goes to 4, so 5 goes to 5, which goes to 4, so 5 goes to 4. So in each case, I started on the left, and I see where I end up on the right, and that tells me what happens under function composition. And so this is one way to compose functions, but again, as you can imagine, doing this for arbitrarily large examples would get kind of hard. So it'd be nice to see how to do this with our shorthand notation. And so what was f again? Well, it is the permutation. Well, let's have you think about it. What should f be and what should g be? I'll give you a good 10 seconds. Well, we see that 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, and 5 goes to 5, so that's the permutation f. The permutation g sends 1 to 2, 2 to 1, 3 to 3, and it swaps the 4 and the 5. So what's g composed with f? Oh, order matters, so make sure we get it in the right order. Well, what happens to the 1? First, the 1 goes to 2. So what's in the second slot here? 1. So we get 1 back. In general, what you do is, to figure out what goes in the second position, the first permutation, you look at that number, and then you look at the entry in that corresponding position in the second permutation. So I see 4 here, so I'm going to look at the fourth. I'm going to look at the fourth slot in the second permutation, and I see a 5. So that's what I write down. So 2 goes to 5. Likewise, if I'm interested in the third number, I look at the third position in the first permutation. It's a 1, so I look at the first position in the second permutation and see that it's a 2. So that's my answer. Similarly, the fourth element in the first permutation is a 3. The third element in the second permutation is a 3. Finally, the last element is a 5. The last element is a 4. So there's my answer. And you can check that's exactly what I get if I look at the picture. 1 goes to 1, 2 goes to 5, 3 goes to 2, 4 goes to 3, and 5 goes to 4. Yes, it is correct. But you can now do longer permutations with this. So you can see that it's possible to multiply permutations in one-line notation. What should also be clear is that every permutation has, if x is finite, then every permutation has a one-line notation. So that's a fact that's useful to note. Namely, if you decide to list the elements in x in some order, then you could always define the one-line notation to be the sequence sigma of x sub 1, sigma of x sub 2, up to sigma of x sub n. And you can define that to be the one-line notation, like we've been doing. This also tells you that the size of Sx has to be n factorial, because it turns out that there's n possible ways to choose the first element. Then there's n minus 1 ways to choose the second element, because it can't be equal to the first, and so on and so forth. You can start to see that there's n minus I ways to choose the ith element, well, n minus I plus 1 ways, because you have to pick something distinct that isn't one of the ones appearing in the earlier parts of the list. And so by the time you reach the end, you have a list of n distinct objects. There's n factorial ways. So let me bring the stuff we've been talking about back to our card deck problem. Let me do a small card deck. Suppose you have a card deck of only 6 cards. Then what happens? You cut the deck in half. You get the first 3 cards together and then the second 3 cards. And when you do this perfect shuffle, you're going to alternate 1, 2, 3 in the odd positions, and 4, 5, 6 are in the even positions. Well, if you write down the permutation representing where your cards end up going, the second card ends up in the 3rd slot, the 3rd card ends up in the 5th slot, the 4th card goes in the 2nd slot, the 5th card ends up in the 4th slot, and the first and last cards stay where they are. And so this permutation represents where the cards end up after one shuffle. And so if you square this permutation, you get where the positions of the cards end up after 2 shuffles. And when you cube this permutation, you get where the cards end up after 3 shuffles, and so on. And so taking powers of this permutation can be useful for card tricks to figure out where certain cards end up in your deck. But for our case, the question was how many shuffles before you get the deck back to the original order. The answer ends up being the number of shuffles to reorder the deck is actually just the order of this permutation as an element in a group.